All right, in this lecture, lecture 20, we will focus on the strong Markov property. Let's begin by discussing n-step transitions. For a time homogeneous Markov chain, which we denote as x mapping from omega to script x to the z plus, we can define the n-step transition probability matrix denoted as p to the n. Its xy entry represents the n-step transition probability for xm plus n to be in state y, given the event that xm equals x. That is, n-step transition probability from x to y is defined as the probability of the set xn plus m equals y, given the set xm equals x for all x, y in script x and m, n in z plus. As a reminder, the rho p to the n sub x, which is n-step transition probability from x to y for y in script x and is an element of script m of script x, represents the conditional distribution of xn given the initial state, the set x naught equals x. Now let's consider a theorem. The n-step transition probabilities for a homogeneous Markov chain form a semi-group, that is, for all positive integers m and n in z plus, the m plus n step transition probability matrix equals the m step transition probability matrix times the n step transition probability matrix. For the proof, consider that the events, the set that xm equals z for z in script x, partition the sample space omega. Hence, we can express the event that xm plus n equals y as the following disjoint union. The set xm plus n equals y is the union over z in script x of the set where xm plus n equals y and xm equals z. It follows from the Markov property and the law of total probability that for any states x, y, and positive integers m and p sub x y to the m plus n equals the sum over z in script x of p sub x of the set xn plus m equals y and xm equals z. This is equal to the sum over z in script x of the probability of the set xn plus m equals y, given the set xm equals z and x naught equals x, times p sub x of the set xm equals z. This further simplifies to the sum over z in script x of the probability of the set xn plus m equals y, given the set xm equals z times p sub x of the set xm equals z. This equals the sum over z in script x of m step, transition probability from x to z times n step transition probability from z to y, which is the x comma y entry of p to the m times p to the n. Since the choice of states x and y in script x was arbitrary, the result follows. As a corollary, the n-step transition probability matrix is given by p to the power of n for any positive integer n. In particular, for the proof, we have n plus one step transition probability matrix equals n step transition probability matrix times one step transition probability matrix. Since p to the 1 equals p, we have p to the n equals p to the power of n by induction. Next, we define the probability mass function of a time homogeneous Markov chain X mapping from omega to script X to Z plus at step n. We denote this by sub n, which is an element of script m of script X. Now, let's introduce the Chapman-Kolmogorov lemma. The right multiplication of a probability vector with the transition matrix P transforms the probability distribution of the current state to the probability distribution of the next state. That is Pi sub n plus 1 equals Pi sub n times P for all n in n. To see this, for the proof, we fix y in script X from the law of total probability and the definition of conditional probability. We observe that P sub n plus 1 of y, which is the probability of the set x n plus 1 equals y, equals the sum over x in script X of the probability of the set x n plus 1 equals y and xn equals x. This in turn equals the sum over x in script X of the probability of the set xn equals x times p sub xy. This is the yt component of p sub n times p. Now let's discuss the strong Markov property or SMP. We are interested in generalizing the Markov property to any random times. For a DTMC X mapping from omega to script X to the Z plus and a random variable tau mapping from omega to n, we want to know whether for any historical event H sub tau minus 1, which is the intersection from n equals 0 to tau minus 1 of the set xn equals xn, and any state xy in script X, we have the probability of the set x tau plus 1 equals y given h sub tau minus 1 intersected with the set x tau equals x equals p sub xy. Let's consider an example, a two-state DTMC. Consider the two-state Markov chain X in the set 0, 1 to the Z plus such that P sub 0 of the set x1 equals 1 is Q and P sub 1 of the set x1 equals 0 is P for PKU in the closed interval 0.1. Let tau mapping from omega to n be a random variable defined as tau is the supremum of the set of n in n such that she equals 0 for all a less than or equal to n. That is, the set tau equals n is equivalent to the set x1 equals 0 and so on till xn equals 0 and xn plus 1 equals 1. Hence, for the historical event h sub tau minus 1, which is the set x1 equals x2 and so on equals x tau 1 equals 0, the conditional probability of the set x tau plus 1 equals 1 given h sub tau minus 1 intersected with the set x tau equals 0 is equal to 1 and not q. Let's define this formally. Let tau mapping from omega to n be a stopping time with respect to a random sequence. X mapping from omega to script X to the Z plus. Then for all states X uy in script X and the event H sub tau minus 1, which is the intersection from n equals 0 to tau minus 1 of the set X, n equals xn. The process X satisfies the strong Markov property if the probability of the set x tau plus 1 equals y given the set x tau equals x intersected with h sub tau minus 1 equals the probability of the set x tau plus 1 equals y given the set x tau equals x. We have a lemma that states homogeneous Markov chains satisfy the strong Markov property. For the proof, let x mapping from omega to script x to the z plus be a homogeneous DTMC with transition matrix P, and tau mapping from omega to n be an associated stopping time. We take any historical event h sub tau minus 1, which is the intersection from n equals 0 to t minus 1 of the set xn equals xn, and states x and y in script x. From the definition of conditional probability, the law of total probability, and the Markov property of the process x, we have the probability of the set x tau plus 1 equals y given h sub tau minus 1 intersected with the set x tau equals x is equal to the sum over n in z plus of the probability of the set x tau plus 1 equals y and x tau equals x intersected with h sub tau minus 1 and the set t equals n, all divided by the probability of the set x tau equals x intersected with h sub tau minus 1. This equals the sum over n in z plus of the probability of the set xn plus 1 equals y given the set xn equals x intersected with h sub n minus 1 and the set tau equals n times the probability of the set tau equals n given the set xt equals x intersected with h sub tau minus 1. This simplifies to p sub xy times the sum over n in z plus of the probability of the set tau equals n given the set xt equals x intersected with h sub tau minus 1, which equals p sub xy. This equality follows from the fact that the event, the set tau equals n, is completely determined by x not through xn. As a reminder, consider a homogeneous DTMC x mapping from omega to script x to the z plus and the first instant tau sub k, which is defined as tau to the set y k sub x for the process x to hit a state y in script x k times. Recall that tau sub 0 is defined as 0 and the recurrence time h sub k is defined as tau sub k minus tau sub k minus 1, which is the infimum of the set of n in n such that x sub tau k minus 1 plus n equals y for all k in n. We define a process y mapping from omega to script x to the z plus, where y sub m is defined as x sub tau k plus m for all m in z plus. If tau sub k is almost surely finite, then it is a stopping time with respect to process x. Using the strong Markov property of DTMC x, we will show that y is a stochastic replica of x with x naught equals y. Now let's talk about hitting and recurrence times. We will consider a time homogeneous discrete time Markov chain x mapping from omega to script x to the z plus on a countable state space script x with transition probability matrix p mapping from script x times script x to closed interval 0 to 1 and initial state x not equals x in script x. We denote the natural filtration generated by the process KISS as script f bullet, where script f sub n is defined as sigma of x naught through xn for all n in n. Remember that starting from state x, the mean number of visits to state y in n steps is the expectation over x of n sub y of n, which equals the sum from k equals 1 to n of k step transition probability from x to y. From the monotone convergence theorem, we also get that the expectation over x of n sub y of infinity equals the sum over k in n of the k step transition probability from x to y, from x. If tau sub k minus 1 is almost surely finite, then tau sub k minus 1 is a stopping time for process x. From the strong Markov property of homogeneous DTMC x applied to the stopping time tau sub k minus 1, it follows that the future sigma of x sub tau k minus 1 plus j for j in n is independent of the past sigma of x naught through x sub tau k minus 1 given the present sigma of x sub tau k minus 1. Since x sub tau k minus 1 equals y for k greater than or equal to 2, deterministically, it follows that sigma of x sub tau k minus 1 is a trivial event space, and the future sigma of x sub tau k minus 1 plus j for j in n is independent of the random past sigma of x not through x sub tau k minus 1. We further observe that the distribution of sigma of x sub tau k minus 1 plus j for j in n is identical to the distribution of x given x not equals y. Thus, the process x sub tau k minus 1 plus j for j in n is distributed identically for all k greater than or equal to 2. We observe that the recurrence time satisfies the condition that the set h sub k equals n is an element of sigma of x sub tau k minus 1 plus j for j in the range 1 to n for all n in n. Hence, the recurrence time h sub k is independent of the random past sigma of x not through x sub tau k minus 1. Recursively applying this fact, we can conclude that h sub 1 through h sub k are independent random variables. Further, since x sub tau k minus 1 plus j for j in n is distributed identically for all k greater than or equal to 2, it follows that h sub k for k greater than or equal to 2 are distributed identically. We have a lemma. If h sub 1 and h sub 2 are almost surely finite, then the random sequence h sub k for k greater than or equal to 2 is IID independent and identically distributed. For the proof, from the above two remarks, it suffices to show that each term of the random sequence tau mapping from omega to n to the n is almost surely finite. We will show this by induction. Since tau sub 1 equals h sub 1 is almost surely finite, it follows that tau sub 1 is a stopping time. Since tau sub 2 equals tau sub 1 plus h sub 2 is almost surely finite, it follows that tau sub 2 is a stopping time. By inductive hypothesis, tau sub k minus 1 is almost surely finite. Hence, h sub k is independent of h sub 1 through h sub k. This should likely be h sub k minus 1 and identically distributed to h sub 2 and is almost surely finite. It follows that tau sub k equals tau sub k minus 1 plus h sub k is almost surely finite and the result follows. And that concludes our proof and the lecture on the strong Markov property.